It should be another draft physics video presentation. So I'll catch up on some stuff. Little incidental links from other people that were in videos that didn't, finish properly or some other excuse, and so I'll just go over them again quickly, just to be fair and such. So somebody linked to this. Light seems to pass through solid metal. So what they do is take a very thin piece of metal and they poke a bunch of holes in it. And they're not randomly spaced, they're very precisely spaced in terms of their equidistant holes. And they don't shine regular visible light, they're shining infrared radiation heat, essentially. And remarkably, most all of the heat goes through. So in spite of the fact that there's, metal in the way, it behaves as if there's no metal there. And you can sort of understand that that's a way to explain it. And the one way they don't explain it is as, obviously when you poke these bunch of holes in the surface, you're making the metal part, smaller and smaller, or weaker. The tension between the metal isn't as complete between the atoms. And so just as you could imagine poking your finger through something that has a bunch of holes in it, it's easier to poke your finger through it. It's likewise easier for this piece of metal to move because it's not connected as securely to the rest of the metal. It just doesn't have as many connections, so it's not as rigid, so it can vibrate. Essentially, you could argue it can move. The energy isn't displaced quickly enough. That is, it doesn't move out in these directions as quickly because there's fewer of these directions. And so the energy is in the one little piece, and the one little piece gets thermally equalized, and the energy ends up going through it. So it's, not that interesting. It reaches thermal equilibrium quicker. And that's really all you're really saying. And so it's essentially pushing on the other side as hard as the other side. So I'll get to that part because that sort of is interesting. But I'm just saying there's no conversation in the paper about the fact that it's not about the holes. It's about the size of the pieces of metal now. They don't talk about they never talk about essentially what's happening in the background. They're always focused on one thing and they just ignore the rest of the circumstance. Just as when there's a slit experiment, they just kind of ignore the fact that on the nuclear level, there are no such things as surfaces. On the nuclear level, there's just electrons in space, and there's a proton maybe here, and there might even be another electron over here, another one way over here. That's what a surface is. A surface isn't some straight line in space somewhere. And this goes to the whole principle of interferometers, as I pointed out, and the fact that you can't measure 1/10,000th of a proton with something that you can't even tell how far your light even went into the mirror, because it's going to be variable, because the surface is variable. All right. So the point is that all these experiments take place and nobody really picks at them. It's not put up to some, let's all as thinking people speculate on why there's a phenomenon. Instead, a little select group, the group that did it, they have a point of view, they want to push a certain point of view, so their explanation is heard. All the other explanations are never heard. So there really isn't any open science taking place. It's all a bunch of agenda science. All of the experiments are essentially quote mined in terms of interpretation by the person conducting the experiment and their objectives, their point of view, which I would argue is biased by something they wish to confirm or something they wish to refute. And it's just not very good physics. I'd say better physics happens on this channel because obviously scrutiny happens. The complainers complain. Unfortunately, they can't do it without being rude, and so it sort of spoils the fun. But nobody seems capable of doing this without rudeness thing. So I'm searching for, where the hell is it? No, 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 no. Yeah. That was alright, this is the image file. Yeah, there should be one here on, oh, maybe I didn't go back far enough. Maybe. No, space-time crap. Fundamentals, this is it. Alright, so another guy linked to this video that just has some, it's an old 50s style video pointing out different antenna features. I mean, there's a very interesting subject, antennas, how they work, what's exactly happening. And so I'll sort of get onto some of that. But what they were saying here was just so deceptive in the way it was stated. So the idea is the two little dots are representing two different antennas. And if you put them out of phase at certain distances, you'll be able to create interference in one direction and no interference in the other direction, and you can make your antenna directional, which is perfectly true. But they implied that by doing this you could increase the range of your antenna, and you won't increase the range at all with this technique. So in that sense, very deceptive. What they could have done is separated these two antennas much further, and then they could have created the interference pattern, but they didn't even go into that. So I'll just play a little bit of
80
this.
degrees out of phase with each other. The waves propagating in this direction thus cancel each other out.
So you can see it moving. So this is all true, good physics. Yes, one direction you'll have some cancellation. Obviously in some angles there won't be cancellation, complete cancellation. Some angles you'll get some signal, so it won't be a perfect destruction of receivability in one direction or receivability in another direction. But it's just about receivability. You can't destroy the energy. So the energy is still going in all directions, and you're not getting more energy in a particular direction unless you put twice as much energy for two antennas. So obviously if they're 500 watt antennas, both of them, then you have 1,000 watts, and yes, that signal will go further than a 500 watt signal, but it's like more energy in, more energy out, of course. But there's no increase in the direction out. I mean, there's no increase in the depth of the signal. So they're sort of implying, and it doesn't state it, but they imply that somehow you're focusing the signal in these directions, and you're not. You're not creating more energy in a direction. You're just creating more energy if you have more wattage, period. So let's play a little bit of this. Alright, so so the idea is first you can make the signals go in these, you can either go this way and this way with the signal, or this way and this way by changing the phase, or changing the distances. And the signal can be directional in that sense. By directional I just mean it goes more, you can receive it over here, you can receive it over here, but this way it's not receivable, because the ons are on top of the offs, which are just negating the ons and the offs. You just don't have any clear picture of on off, because the on is on top of the other one's off, so to speak. So you've neutralized the pattern by putting a white dot on top of a black dot. Put a white dot on top of the black dot, there's no black dot. Right? It's not that complicated. Alright, so here's where they get into what will really magnify. So you have to put a lens on. You have to use a parabola or some other, you can do it with non-parabolas. If you come from some obscure angle, then you can use some other shape. But the idea is you'll reflect the energy off of essentially a mirror in one direction. So you can have your antenna, and then you put a mirror behind it. Obviously all the energy going this way, you can reflect it back out this way, and so you'll get true directionality, which will increase the depth of your signal. So the only way you can make the signal go further is you have to take the stuff going the wrong way, and you have to reflect it at the right wavelength distance, so it's on phase, and send it in the direction of your signal. So your signal has a phase like this. Well, that's not a very good drawing of a phase, but whatever, it'll have to do. And so you want to have it bounce off this signal so it comes in phase. So when it reflects back, it's still in the right phase, and that's the parabola. We'll do that from a center. So anyway, so that theory is perfectly good. And so they're confusing, or combining these two subjects and implying that the other way of manipulating antennas, that is putting antennas in rows or doing all this other stuff, actually can do this magnifying thing, which it can't. So I thought that part was quite deceptive. So they sum up with some kind of statement like that. It's just very, just play a little of it.
Simple principles facilitates the design of antennas which concentrate energy and increase receptivity in the desired direction.
Right. So he sums up with that statement as if that first bit of antenna array could concentrate. It didn't do any concentrating. The only kind that can concentrate are the parabola type, the reflective type antennas. So, that was just pretty deceptive. All right, so anyway, on the subject of antennas, there's this whole, how does it really work? And I can't say for exact certainty yet, but I'm pretty certain about some things. So the idea is you're pumping a signal in to the antenna, energy, and on-off, so there is stuff, and there isn't stuff, and then there is stuff, and then there isn't stuff, and there is stuff, and there isn't stuff. And the idea is the stuff is moving the speed of light, so we can call it a force. We can just kind of understand that there's matter and then there's force. Okay, the force goes the speed of light always, and the matter goes, that's the tricky part, right? Because what we're calling matter, all right, is configurations of matter. So this is where the whole, they use the word particle, and it doesn't really mean particle. It means a group of particles. So we know that an atom is, a combination of particles in a configuration. So how do the particles move versus how does the entire atom move? It's like the difference between how a fish moves and how a school of fish moves. They're not the same thing. They don't move the same way. Not that much similarity. Oh, Jesus. Stop it. I move my feet, I touch the wire picks up noise, blah, 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 blah. Stop that. Anyway, sorry. So this is where, you have to understand, when I say matter, I suppose the default for that word is electron, okay, or proton. Oh, damn it. All right. That in? Well, you can't really see that very well, can you? My fault, probably. I was quite comfortable. I don't like having to get uncomfortable just to make things viewable. All right, so anyway, back to the story. So the idea is that we're putting energy, and the energy is in the force form. Now, it could be that it's just transferring the force between here's an atom and here's an atom and here's an atom inside the material, and the force is really just going between the atoms. It's being exchanged by movement. And that's the real question. But the idea is that the antenna, you could think of the antenna as being something that oscillates in its size. You could just think that it goes from being this size to big, this size to big. Now the question is the opposite thing, where you could say, okay, I'm going to make the antenna smaller by sending a negative current in. But that's just a relative conversation. But you're really saying this would be the negative, this would be the positive, these two positions in space. And that the idea is this stuff comes in and it actually does push, okay, and pushes. And the pull back would be the opposite force of the protons and pushing the electrons back into the surface. and that the only way you could do that is to pump in more of that like proton energy, to be truly negative. But I would argue that most signals don't have a true negative. They just go from ground on, ground on, ground on. They're not going ground negative. They're not going from a positive voltage to a true negative voltage. They're just oscillating an on voltage. So it does make it a little more complicated. But the point would be is if it's a negative voltage, it pulls the electrons in. If it's a positive voltage, it pushes them out. Now obviously positive is the wrong way to say it, right? Because plus and minuses are wrong in physics. But the idea would be, yes, a positive voltage pulls in because it's negative to the electrons. It causes attraction, and it causes repulsion. If it's a negative voltage, pushes the electrons away. Positive voltage pulls them in towards protons. That would be the simple argument. All right, and so you could see that if this antenna did do that, and if this surface moved at the speed of light, that is, if it moved the same speed as the force, that is, the electrons move from one position to another position at the speed of light. So the electron was here and it moves here. You could sort of understand if it does that at the speed of light, the speed of the force, the same speed as the force, that just this position change, if you understood that the universe was sending radiation in all the time, so it's sending force at the antenna all the time, you could sort of understand just changing the position, right? When the electron's moving this way, it'll reflect nothing. When the electron moves out, it reflects everything. Okay, so everything between this point and this point, right? When the electron's moving this way, every single one of those bits will be reflected back to the world. And when it's moving the opposite way, nothing can reflect because it's moving as fast as the force. Now, even if it didn't move as fast as the force, this would be true. So I probably should draw that. So I just want you to get the idea that the antenna is working two ways. You could say this force that's coming in is when it's pushing the electrons out, well, the force is also going out, and it's also pushing the electrons out. So you have not only the force going out, but you have the electrons going out, which means they're going to reflect because they're moving into the field. So they're going to push these reflections also. So you're not only sending energy out, you're also sending more energy out in the sense that the electron's changing its position, it's moving into the force, and that way it's reflecting more of the force. So you have the reflected component plus the energy component itself, and they would be in phase and they would be in the same direction. Alright, so what I sort of wanted to get to was just this way of modeling the basic function, way of understanding it. So I'm not, this is draft, just something I've been thinking about is the internal mechanism of an electron, let's say. And so I've thought of the idea that it has just a piece of energy in it, and it's trapped. And the energy can just bounce back and forth. That's all it does. Bounces back and forth. And so then if I put a field of energy around it, right, the idea would be, okay, is that it would gain a bias in a direction. So if I hit it from a direction, I'm going to change this direction. So, whatever plane the electron is moving in, it's going this way and this way. So it goes a little this way. Well, you could say it goes this way, then it goes back this way, and it goes this way, and it goes back this way. But it has to have a bias because there has to be a first, right? So we're back to this argument that it really goes 1 0 1 0 1 0. The first act is always the first act, and then it stops, and then it goes, and then it stops. There is no permanent stop because you're always reflecting. So whatever first went in is the first cause. And so you could argue that by interacting with the field, it just changes the first cause. It's still going to oscillate in a direction, because there's a 1 is 0, a 1 is 0, a 1 is 0. But yeah, see, it always ends up getting a little bit confusing. Alright, so I'll go back to the bucket analogy and just see if that. The point is if the energy went in first this way, that means the box would move this way, right? So when it hits the box, the energy moves it this way, right? You can get that. And that means this back end moves closer. So when it reflects, it only goes back this far for this amount of time, right? But when it does hit this back surface now, it stops. So now it stops. So I don't know how to draw stops, but it stops. So while the arrow is going this way, the front of the box is still moving, the back of the box is moving. The whole box stops in this new position, and now the arrow is going to go that way. So the box isn't moving while the force is moving forward. Then when the force hits the front of the box, well, now the box will move, and now it will move the whole time the arrow is going the opposite way, and so on and so on. So the box would just jerk its way through space. So that would be the point, is that the electron is just jerking at the speed of light. Goes this way, and it stops, and then it can go this way, and it stops, and it can go this way. So it, even though the arrow is reflecting, the first cause is its direction. And so what happens when this field comes in is it's going to change the first cause. It's going to change the direction. Instead of the arrow moving back and forth this way and going this way, it's going to move back and forth, and say an arrow comes in this way and hits, it's going to move back and forth in some mixture of those two. That direction plus this direction equals yeah, what direction does that equal? Not something like this direction. So now the first cause is in this direction, and so now it jerks through space in this direction. Now when it moves into the field, this is where that drag thing comes in. Drag is going to try to you're going to hit more energy coming this way if you're moving into the field this way, just like the reflection argument. So now if you're going this way, you're going to jerk in the direction of this more energy, and that's going to eventually stop you, theoretically, or it's going to compress this box, compress the size of the box. That means there's more interactions from the front and the back, so it jerks faster. So you change how fast it jerks, not how fast it moves. I mean, it will change how much space it covers in amount of time, but it's not changing how fast it moves each time. And so then it's going to be jerking at a different rate. As it hits, it jerks quicker but moves less distance. So as it goes slower, it essentially pushes in a direction. As it goes slower, it pushes in a direction, its frequency goes up. And the frequency is what might be what we could term light. The frequency at which the electron is moving, that is the speed, is tied to its frequency because of this circumstance. And this circumstance, as you slow it down, you increase the number of interactions and you increase the frequency. So as the force opposes the motion by drag, it doesn't necessarily stop the motion, it only increases the frequency. Yeah. Be one way to say it. So anyway, this is, like I said, I have to really go through this and think about it in terms of, modeling it. And it's another way of modeling the motion of an electron, because in this simulation now it is working, as I did show. I should show some more of that, frankly. In the sense that I've got the particles moving towards each other and creating the proper arrangement. That is, the proton and the electron do attract, and the electrons do repel, and so the protons repel, and so it is working. But the motion is the tricky part, like how it moves. And so the real point I'm trying to make is if we understand that it can only move in increments of the speed of light, then all we're saying is how much space does it consume per one of those bits of motion, and the amount of space between the motion would dictate what it reflects to the rest of the universe, also based on what the universe is hitting it. So again, it's the simplest way to illustrate this. Yeah, there's no other way to illustrate it except just to draw the idea. Just get the idea that if I move an object at the same speed as the force is hitting it, you can just sort of understand that as this object goes from this position to this, from A to B position, none of this force, if it did move at the speed of light, none of this force could hit it. Now obviously if it stops, then the force will hit it, and then it's going again, and then the force will hit it. So you could almost argue that these could be harmonic frequencies. That there's a real speed that it gets from point A to point B, and the only way it can get the only way this real speed can be the speed of light is if the motion hasn't encountered drag yet. That is, it hasn't interacted with enough of the field to be stopped. So it's able to move until something acts on it, a force acts on it. The more force acts on it. Well, anyway, I don't want to even get in. That's just too complicated. So let's just stick with this basic analogy. That if you could understand that this, like say, even if it moved only half the speed of light, you could still understand that the force coming from the two directions would be behaving quite differently. So if I'm moving this from here to here, and I move it at half the speed of light, it means that only half of this stuff is going to get reflected, on average, because it's moving in the same direction the force is moving. So obviously the stuff can't reflect as soon as it would if it stayed at A. If it stayed at A, we know it's going to reflect here. If it moves to B, we know it's going to take much longer to get to it before it reflects. And if it moves there at half the speed of the force, well then it's going to be half as much reflection. And this opposite is going to happen on this other side. So if I'm going half the speed of light into the force, then I'm going to get twice as much energy back, right? Not 1.5. So instead of having 10 lumens or 10 watts of energy going this way from reflection, you'll end up with 15 watts because you've moved this to a new position, and so you have a place where in space the reflection's coming back at you, so you're observing the reflection. The reflection's going to have a part that's going to be 15 watts, and then it'll have a part, if it moves back, where you understand that it's going to be 0 watts. Well, it won't be 0. It'll be half of 10. So it'll be 5. And then it'll go back up to 15 watts. And then 10. And obviously that's a signal that could be received by something. Something could tell the difference between 5 and 15, and 5 and 15. So that's all you need to create all these frequencies that are so critical to the function of everything that's talked about. But why just moving an electron automatically sort of creates a photon? I mean, in the sense that it creates a frequency, and if it's done enough times, right, this is the critical part, right? They never talk about the ray length of light. They just show you this stupid picture of these two waves, and they never say anything about how long it has to be, when length does matter. Okay, it really matters. And it's really important that enough of this happens, not only for our electronic detectors, they need a certain amount of it, but our eye certainly needs a certain amount of it, that is length of it, to say that was a photon. And they just don't talk about that at all. And then how the energy of the photon really does you can sort of understand that if this is just one clump, you call that a photon. Well, what if I gave you 15 of those? Say there was 15 of these wave lumps. Am I going to call that also a photon? I mean, it's kind of obvious that you'd have to break it into some sort of, like, that's 2 photons, because you got, twice as many little humps. So, but physics just doesn't deal with that concept at all. And I would think logically that it's a critical to the whole idea of what we receive and what we call a photon. So again, in the polarizing experiments with light, you can just sort of understand that the energy isn't destroyed going through the filter. There is no destructive interference with the polarizing. The polarizer is just changing the phase. So it's changing light we could see into light we can't see by putting it out of phase. It's essentially creating destructive interference, is what their word is, but it isn't destructively anything. The energy's still there, and you can reconvert it back into a form that you can see. You can, the same numbers are always there. There's always the 20. Okay, there's always the 20. And whether I mix it 10 and 10, well, 10 and 10, I'm not going to see the difference, right? 10 plus 10 is 20, and I won't see it because there's no difference. There's no change. But it's still the same amount of energy. You just, like I said, polarizing filters are just phase filters. That's what they should be called. They're really not concerned with the polarization of the light. They're more concerned with the phase of the light. And they're changing the phase based on the polarization. So based on its angle, it gets more phase changed or less phase changed. So if it's coming in this way, it gets, completely, all of the bits get phase differential. I mean, the A bit, like if you saw it, A, B, C, D, E, F bits, all the bits end up getting different phases. If it goes through this way, well, they'll all get changed to plus phase, or changed to, or left minus phase. There will be no, all they'll do is change the frequency. They'll just change it to this instead, but all of them will still have the same frequency. I mean, the same distance between them. So it won't change the phase of the string of photon, the string of energy. It'll just change them all or change none of them, and the other one changes all the little bits. So this one has a this one's phased back, this one's could be phased forward, this one's phased, well, you can't phase forward. You can only slow down the bits, you can't speed them up. So, and then this one's held back, so the photon ends up having only 2 clumps to it, because this one, and this one had their phase changed. But anyway, that's another subject, really. And do I want to go, how far do I want to pursue this? Yeah, so anyway, like I said, it's a lot of moving pieces. You have to kind of think about, something moving into the more force. What's the consequence of that? And then you have to go back to understanding, well, it doesn't change the fact of what direction it moves in. It only changes what speed it moves in that direction. So it'll still move in the same direction as it meets more force. See, I just what I just said. It will change the speed. It won't change the speed because it will jerk less distance, but it'll do it more often because there's more reflection. So the smaller you make this box, the more interactions you're having. So they're happening more frequently. So you're moving less distance per little dotted line, but you're moving dotted lines more often. So it ends up being the same amount of velocity overall. So you can't change the velocity. So that's the key component. So it really does move a constant speed, because you're not changing the overall distance it will move. You're just changing in how many steps it does it. But it's still the same amount of the same amount of time on as off, in the sense that as I make the box smaller, I'm making it smaller in a bias, with a bias. That is, I'm making the time it spends off. This way, I'm making one direction happen less and less amount of time. So it's like, so I'm just changing the amount of time it spends not moving. So you could just say the dotted line stays the same. Well, it does get smaller. What I'm really changing is the amount of time it spends not moving. So as as this line gets smaller, the amount of time it's not moving also gets smaller. So the overall distance and the amount of time remains the same. All right, yeah, that's how it works. So anyway, yeah, it's probably too many moving bits to. I'm just saying that it's an actual answer to the question, rather than just saying bent space or virtual photon. It tells you why moving an electron changes what's reflecting to the rest of the universe. So it sort of explains the little thin film I was showing before. You could just understand if you are literally moving electrons on the surface and bulging them on the surface of a piece of metal. So here's a piece of metal. I've hit it with energy. I've pushed the electrons on the inside. That pushes them on the outside surface. So this stays the same. You're taking this bulge, this movement of electrons, and you're just converting it to this surface. And you could understand that if there's energy coming in this way, I've moved the surface, which means I'm compressing the amount of space the reflections will happen in. So now there's going to be places, if I keep oscillating this, there's going to be places where there'll be a lot of reflected light, and then places where there's less, and then there'll be places where there's a lot, and places where there's less, and places where there's a lot, and places where there's less. And that simple process of hitting it with energy, again, infrared. So I'm hitting it with infrared radiation, a frequency, and it's moving here at that frequency. And by moving this surface back and forth, I end up creating this pattern. Seems pretty logical. And obviously where the holes are, it just goes straight through. Alright, well, anyway. Yeah, I'll leave it at that. I figured this would be a little bit awkward and challenging to get into, just because it's not counter to my own theory. It's just a way of making the mechanics even simpler. Going a step deeper to figure out what an electron is actually doing, and all it really is doing is being forced to change its direction. It always wants to go somewhere. It's always going somewhere, and the force just keeps changing its direction evenly. So if it's in the universe, very far away from anything else that can influence it, the energy's coming equally from all directions. You could see that it would just keep changing its direction and not end up going anywhere, because it's changing its direction all the time. It would just sit there spiraling in a circle, because its direction would keep getting changed evenly, and so it couldn't get anywhere, couldn't progress anywhere in space, because the pressure keeps pushing it. So this is almost getting back to an orbiting sense of electrons spinning in circles, but they're not spinning in circles around the proton. They're spinning in circles in the space they occupy. Alright, probably enough. I don't want to get too blah 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 blah. So yes, no useful comments. videos for the critics to deal with: the question video and the experiment video. In the titles. Yeah. Anyway, till the next time and such. I think I'll leave it there.